Hello everyone, thank you for tuning in. My presentation will be about how to calculate the center of inertia, frequency, and system RoCoF using PMU data. I'm Shutang Yu from the University of Tennessee, Knoxville. And the first question comes to us is what's the system frequency? This may be an invalid question because it's just like asking how deep is the sea. The frequency is usually a localized measurement data depends on where you measure it. And that's a definition called center of inertia frequency or COI frequency. The COI frequency is defined as the frequency value weighted by the inertia at different locations in the power grid. It may be used to represent the system frequency if we assume there exists one. On the right, the video showing how the system frequency look like, and also the frequency measured at different locations will look like. If an event happens in the system, we can know that the system frequency need to consider the frequency environment at all locations, especially during the changing stages. And here's a proposed method to calculate COI and the RoCoF. And we know that the start of the frequency event, the COI frequency is influenced by two factors. One is the system inertia, the other the event magnetic amount. There are some other factors like the governor response and load response because they are deadband, there are deadband, and also the delay of the governor response, and also the initial frequency duration is very small, so we don't conclude, so we don't consider the governor response and load response. And with those two assumptions, we can know that COI frequency is a constant value at the initial time after an event happening. And we can borrow the weighted average frequency of the COI frequency definition. The objective becomes to find the optimal weighting values for each frequency measurement. And here's the approach we developed to find the weighting factors of this frequency data. For example, we have n different frequencies, f1, f2, and fn, and we assume n different weighting values for each frequency. And for each timestamp tk, we can have an equation like this. F0 is the start of the frequency at the start of the event, and delta f is the frequency decline at each timestamp during each time period. And we can have a lot of equations if we have multiple data points. So we can have a set of equations, then we can solve these equations using the alternate least square method to find the weighting value for each frequency. And after we find it, we can obtain the COI frequency and also the RoCoF. And here's the results showing how the method performed in the actual event. Here's an event happening in Florida. We can see the frequency environment shows a lot of oscillations. And if we use, for example, median frequency, we can find the median frequency of the system has a lot of oscillations, and also there are very deep slope at the beginning of the event. And if we use the COI frequency, we can find it's free of oscillations, and the slope is also smaller, which is closer to the actual system frequency. And this is the conclusion in future work. We proposed a new method to calculate COI and RoCoF frequency of the large system, and it has potential applications in event magnitude estimation and faster control of system frequency, etc. And the future work will be considering some impact factors like the governor response and also load damping. And we also think that the time window selection may impact the accuracy of the approach, and also it is also it may be possible to use the multiple events to calculate optimal weight. Thank you for your attention.